Okay, welcome back. This is Calc 3, 14.3. And the last section, I haven't been doing a lot of integrals, but if you had been trying them like on your own to do the integrals, you know things like this are kind of a nightmare, right? So that you have all these square roots floating about. If you remember Calc 2, the kind of way to get around square roots was to go to the polar graphs, because the graphs for circles in the polar coordinate system are really, really simple. Okay, okay, so that's kind of what we want to do here, and it'll eliminate all these square root issues in our integrals. If we're integrating over top of a circular region, it's much easier um, to work in polar coordinate systems. So first we want to remind you of how to graph in polar coordinate systems and how to integrate there as well. Okay, so this is just a warm-up to 14.3. In particular, we want to work with some polar graphs. Okay, so probably the most important thing to review firstly is the coordinate conversion equations for working here. And we can look at the xy plane and describe any point in that xy plane with an r and a theta, where r is a directed distance and then theta is a directed angle. Okay? So this length here would be r from here to here, and then the angle theta is right here. So going from here to here is some angle theta. In this direction it's positive, in this direction it's negative. And on the arm, there's that concept as well. So if you go in this direction, it's positive. If you go in this direction, it's negative. Okay? These points are non-unique. All right, so we want to be able to go back and forth between that system and the XY system. Okay? And we can accomplish this using trigonometry. So recall that the cosine of theta as the ratio of sides of a right triangle will be adjacent over hypotenuse. So we could say this adjacent side is some length x. So I'll have x all over the hypotenuse, r. And then we could solve for x, and we get our first coordinate conversion equation, x equals r cosine theta. You could do the same thing with sine. Sine theta equals opposite over hypotenuse. Okay, so we're working with this right triangle. Opposite over hypotenuse, so in this case it'll be y over r. So opposite over hypotenuse. And if you, again, multiply both sides by r, you get an equation for y. Other equations you can get, well, the Pythagorean theorem, right? X squared plus y squared is r squared. Whoops. And also from tan, right? So tan of theta is equal to opposite over adjacent. So that's equal to y over x. Okay. Okay, so I hope you remember this. I have it all memorized, and if I need to use it, I can just kind of populate it from this picture here. Sometimes I forget is it theta r or r theta. Usually it's not an issue though. It's r then theta. Okay. Okay, so I need to be able to now graph these things in the xy plane, and the simplest graph is the graph of a circle. So we'll say r equals 3. Okay? So for the polar graphs, you're going to use a polar graphing paper, basically. So instead of having a bunch of rectangles drawn out, you're going to have a bunch of circles with lines through them. Okay? And it will look like a bit like a pizza type deal. Okay. So it's populated with a bunch of concentric circles and then sort of angle lines to help you go around. So this would be at pi over 4 in this, the way I've drawn it. Usually they'll add in, pi over 6s and then the pi over 3s. Okay, so that's our polar graph paper. To get the graph of the graph of r equals 3, I can move this thing with regards to theta. Right now there is no theta, so theta can vary over the real numbers. Theta can be any angle I want it to be, right? So any angle I want it to be. Maybe I should put a little hole in this thing. Sorry, I should have thought of that. Okay, well, oh well. Right, so r equals 3 means set the arm to be equal, the distance on the arm to be equal to 3. So you can go out 1, 2, 3, and you kind of put a pen right at that point. And then let theta vary over the real numbers. So the thing that's getting traced out then is this circle with radius 3. Let me put that in red. Okay, so again, what am I doing? I'm letting R be set at 3, and this is the positive side of my arm, and this over here is the negative side of my arm. Okay, so I'm letting theta vary over all the real numbers, but I have my arm set at 3. So as I do that, as I let theta vary, the curve that's being traced out is just this circle, right? It's this r equals 3 circle. And I can draw that in. Okay, this is kind of like the equation of a horizontal line in the xy plane. It's the simplest thing you can do. The formula is just a number, okay? So awesome, there's that. Okay, and the xy plane, of course, the formula has square roots in it, and it's just a nightmare, right? So this becomes real good. And in general, then we'll say kind of our first type of important polar curve is just the set of curves r equals a, and of course a is going to be greater than 0. If a equals 0, that's just the point here at the origin. Okay. Okay, so this is circle radius a. And when a is equal to 0, that just is going to give you a point. That's just the origin. Okay. The second most important curve that we integrate over is the sort of shifted version of a circle. So the second guy, you'll see it in the forms r equals a cosine theta or r equals a sine theta. Okay, so in particular, let's look at r equals 3 cosine theta. And the way I usually do these is to make a graph of 3 cosine theta, or you can make a table if you don't like making graphs, that's fine too. Do a little table. The amplitude is 3, and then the cosine, I'm just going to do one period for, okay? So I chop the period into 4 parts. The period is 0 to 2 pi. That's traditional for cosine. So this will be pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, which is 2 pi. And the cosine kind of looks like the handles of a motorcycle. Okay. Right? Okay, so then I use this graph, which is in the theta comma r plane, in order to create the graph in the xy plane. Okay. So I go over here to my polar graph paper. I'm going to need 3 sort of guide circles on there, or tick marks in this orientation. Okay. And if you need little helper angles, you can put some in. I don't think we'll need them, but there they are. Okay, okay. And now I'm going to set my arm. I start at theta equals 0, which is right here. This is theta equals pi over 4, theta equals pi over 2. Okay. So starting at theta equals 0, the R value, the arm is up at 3. Okay, so the R value on here, I'm out at 3. I'm here at the point 3. I'll put it in red again. Then as theta goes from 0 to pi over 2, right here, you see the R value is dying down to 0. And what is going to happen when you put that on our polar graphing paper is that you have this kind of curvy effect going on. Okay? And it traces out the upper hemisphere of a circle. Okay, so right now I'm at pi over 2. On this graph, pi over 2 is right here, so the arm is at the sort of juncture on my rotating bar. Then from pi over 2 to pi, here to here, I'm going on to the negative side of the arm. Okay, so now I'm going to be going on to this red side of the arm, and the rotating motion again, as I increase from 0 to -3, that rotating motion is going to cause me to trace out another circle like this, another hemisphere of the circle like that. Okay? And I'll be right here. Okay, then from pi to 3 pi over 2, I go from -3 back to 0. So right now I'm on this side of the arm, the negative side of the arm, and I'll be going from -3 back to 0 once I get to 3 pi over 2. Okay. And what I'm doing now is retracing the graph. And this is a big issue for us in calculus because we don't want to over trace because it will screw up our integral. Okay, we'll want to find the area in here, and if you over rotate, you'll be finding too much area. You'll be double counting the area. So you kind of need to be able to do these by hand for that reason, because your calculator isn't smart enough, well, at least my calculator's not smart enough to know that I need to know where the boundaries are on my area. Okay, it doesn't know that. It's not smart enough. Okay, but for this kind of curve, it's usually not from 0 to 2 pi, but from 0 to pi. And that will trace out this circle here. The other kind of important curve in this section, for the section I have here at 2, is the a sine theta version. So this is r equals 3 cosine theta. For something like r equals 3 sine theta, our r theta graph is going to start at 0 and then increase to 3 and then die down and then go back up, right? So on this polar graphing paper, what's going on? Well, I'm starting now at 0. I start at the middle, and then it's going to rotate around over to 3 at pi over 2, right? So the end result will be this curve here, and then from pi over 2 to pi, it'll trace out the other half of the hemisphere as it dies from 3 to, as it goes from 3 to back to 0, okay? Okay, so this graph is always going to be like this, and then this graph here is always going to be like this. Okay, the types of graphs in section 1 and section 2 are typical. They come up over and over again. Okay. There's also rose petals in there, and maybe we should take a look at one of those. There's limicons as well. I do videos on calculus too, and that's chapter 10 if you need some help with those kind. Okay. These are pretty typical regions though that to integrate over. The circles are usually the headaches. Okay, so anyways, let's talk about integration of these curves then. So section 3, to integrate this thing, you have to, instead of using little rectangles for the regions, you're going to use kind of circular uh, circular regions, like little things like this. Sorry. Okay. For my formulas, I'm going to need the area of this region as opposed to the area. So in Calc 1, you would be finding the area underneath the curve by splitting it up into a bunch of rectangles, and then finding the area of the rectangles and having the Riemann man run across in this way. Now we're going to be splitting up our polar regions into a bunch of these things. Okay? So here is a polar graph, sort of a generic one, okay, going from this angle alpha to this angle beta. And the Riemann man is actually running around in a circle now. Okay? So when you think about the orientation, the bottom curve versus the top curve, if we had two curves, so maybe that curve and another curve here, and I was trying to find the area between them, this would be the top curve, and this now would be the bottom curve, if you think about your Riemann man. Okay, so the Riemann man is going around in a circle. Let me put him down here. Okay. But he's going around in a circle. Okay, so what is the Riemann man putting into his little sack of areas? Okay, his little bag he carries on his back. Well, he's doing a bunch of these things, right? So he's going to be picking up a bunch of these. Maybe should have done that in a different color, but oh well. It's a bunch of these areas. So they're like little pizza slices, if you want to think of them that way. Okay. And then we can think of a generic one in here. Okay. So this particular pizza slice will have a corresponding area, A sub I, that the Riemann man is going to pick up as he runs around the circle. And to figure out the area of that thing, we have to harken back to the times of circles. And I don't know, was Archimedes involved in all that? I don't know. But to find the area of a region like that in a circle, and I shouldn't have filled it in, okay, to find an area of that, we need the, which formula? It's the area equals 1/2 theta r squared, right? In particular, if we went theta all the way around to 2 pi, then this would be pi r squared. So 1/2 times 2 pi times r squared. So it's one way to kind of remember the formula. Okay. So anyways, these A sub I things are based off this formula. So it'll be 1/2 times the particular position of your theta sub I. Okay. Let me think. So this would be located at position R of theta sub I. For the crud. So this theta is kind of a troublemaker. Sorry, it's 1/2. So what would be this angle here? It's a change in theta basically. So like before, it would be change in x in the Riemann sum for finding area underneath the graph. Right? So we would have some change in x. And in this picture, the length here, we're going to call change in theta. And that's going to be this part right here of the area formula. So we would have a change in theta sub whatever I. And then the radius is going to come from this radius function that will be given to you. So the radius function up here was 3 sine of theta. So we would have to take a particular theta sub I. So like in this problem, we were looking at x sub i's, and then its height for our area formula would come from f of x sub I times change in x, right? Now our formula is coming from r of theta sub I times change in theta sub I times 1/2. But it's geometry, really. Okay, and the Riemann man is picking all these up and putting them into his bag and then smoothing it out with a limit as the number of pizza slices goes to infinity, or if you'd rather, as the norm of the angles, these change in thetas goes to 0. So you'll end up with 1/2 times the integral of your radius function, which the book usually calls f of theta times d theta, from whatever angle to whatever angle, alpha to beta. Okay, so there's the formula for determining the area in these regions. On top of that, there's also the difference between two regions. So in general, if you look at this red curve I had in here, right, and your Riemann man needs to figure out the area between the outer curve and this red curve. I'm going to have to kind of really scribble that in to make it clear what I'm talking about. So if the Riemann man needs to find this area, and the red curve is maybe some r sub 1, and then the outer black curve, let's call it r sub 2. The top curve, as he runs around in this circle type fashion, the top curve will be this outer one, and then the bottom curve will be this inner one. Right? So for finding the area between two curves, like this scribbled area right here, it's just going to be a matter of a difference. So it'll be 1/2 integral from whatever to whatever of, I guess in this case we said r sub 2 of theta minus r sub 1 of theta d theta. Okay, so this crash course there in polar curves and calculus. Hopefully that makes some sense. If not, watch my videos from Calc 2 in chapter 10. Okay, and we talk about polar curves. It's like 10.3 or 10.4. It corresponds to the Larson book. Okay. Okay. Let's move on. Now we're in polar coordinate systems doing double integrals over circular regions usually. Okay. Some of the problems in the book will do it over rose petals and limnosons. It turns out for our work in the book, those won't come up very much. Okay, they'll come up in your homework, but that's about it. Maybe if I want to get creative on a test, I'll give you one of those. Okay, but anyways, we're looking at double integrals now in polar coordinates. And why do we do this? Because we want to get away from having to deal with these ugly square roots, right? So if I have a double integral from -2 to the 2, and the inner integral is going from 0 to some y equals 4 minus x squared, and then I'm finding the volume underneath this surface and over top this region. This integral can be nasty to evaluate, but if you go to the polar coordinates, it becomes a little easier. Okay, so that's hopefully your motivation. If we look at this region that's being kind of indicated by the limits on the integral, I'm going from y equals 0 to y equals square root 4 minus x squared. So that's just the upper hemisphere of a circle with radius 2. And then this is the traditional orientation. So our Riemann man would be running from -2 to 2 on the x-axis. And we want to know the volume over top of this region and underneath this curve here, this surface here. Okay, so I don't want to evaluate it doing this. It's going to be a nasty thing. I want to go away from it. So I'm going to convert everything to polar. And I'll let my reader know that. So I'll put a little polar over the equation symbol. And it should be a lot easier, right? So this is the first kind of set of polar graphs, the circle. And the polar graph for the circle here is just r equals 0. So if I now change my orientation, my running man is now going in a circle like this, the okay, so he's going in a circle like that. The inner curve is going to be the point 0, 0, which we said is r equals 0. Okay? And then the outer curve is the curve r equals, well, 2, right? It's just a circle, r equals 2. On the inside, what I'm going to do is use my polar conversion equations to convert this. So I know from the Pythagorean theorem x squared plus y squared is r squared. Okay, so I'm going to turn that into r squared. And then the running man, instead of running from x equals this to x equals that, I'm going from theta equals this to theta equals that. So I have to go from theta equals 0, when I've lost my little graphing arm. I'm going from theta equals 0 to theta equals pi. So the running man is running around in a circle like that. Okay, so I'm going from theta equals 0 to theta equals pi. So that tells me the order of integration. So I'm going, I always do dr d theta. And I left a space because there's kind of a weird mystery right here. Okay. So this isn't a perfect, conversion into this new integral. There's still a little bit to worry about. And to motivate that you into worrying about it, I sort of will set it up as a comparison of the graph paper kind of associated with this region, right? So in the polar coordinate system, when you're integrating sort of over top these regions, okay, so we have this region I'm redrawing with the polar graph paper. And I'm sort of hearkening back to this idea back here in 14.2 when we first developed the Riemann sum for volume. Okay, so we would section up the region into a bunch of rectangles. Here, when we do the same thing, we have to section up the region into a bunch of little pizza slices. Okay, and my point is that it's not going to work in the same way if you're working in the polar coordinate system, because the regions here are not constant, right? As I go farther and farther in the r direction, they get bigger and bigger. If you're just working in the xy plane, all of the areas are the same, supposing you use the same kind of rectangle at each place. So these guys will always be kind of like a sub I equals change in x sub I, change in y sub I. Okay? But these guys are dependent on your r position, how far away you are from the origin. You could just see visually they're getting bigger and bigger, right? Over here, they're kind of the same size in the directions. So the deal is that in order to figure out the a sub I formula, you have to add in an extra factor to compensate for this problem. And that extra factor is going to be a factor of r. Okay, so the area of these little segments is going to be r, change in r, and then change in theta. Okay? So we don't have that problem here, but we do have it here. And there's exercises in the book where they actually have you develop that formula for the area. Okay? But long story short, the regions we're integrating over are increasing with a value of r, so I need to compensate in my integral by kind of inputting r into this position here. So whenever I create my integral and I go from dy dx to something dr d theta, I have to put an r in there. Okay, so it's always dy dx to r dr d theta. Okay, so my integral at the end of the day then for this particular problem would be in the polar coordinate system, the double integral of r squared times r dr d theta. And of course, that would just be the integral, the double integral of r cubed dr d theta, and then we would proceed accordingly. Okie dokie. So hopefully that makes some sense. Let's actually look at one and see how it works, right? So here's number 17 in the book. And they're giving you a double integral in x and y. And it's a nasty integral with some square root stuff. It's really general. So instead of just having r equals something, they're having an a value in here instead. So y and then dx dy. And I'm going from 0 to a. Okay, so first we want to figure out what the region is. So we're here in the xy plane. I'm going from x equals 0, which is the y-axis. And of course the orientation in this problem is the non-traditional orientation, going like this. So I'm going, the bottom curve is x equals 0, the y-axis, and the top curve is this thing, which is the right hemisphere of a circle. Okay, and I'm going to have to draw over my running man. And then on the y-axis, I'm going from 0 to a. So that's going to go from 0 to a like that, and the region will be this region here. Okay. I need to convert that into polar. I'll just put P for polar. Okay. And this time it's just a circle with radius a. So I'm going the Riemann man, and the circular orientation now is thinking of integrating from the bottom curve, which is the inside of the circle, which is 0, to the outer curve, which is r equals a. And then the running man is running from angle 0 to angle pi over 2. Right? So angle 0 to angle pi over 2. And then for the inside of my integral, y from the conversion formulas is r sine theta. And then we always replace dx dy with r dr d theta. Okay. Okay, so now I need to integrate this thing. And it usually turns into a trigonometric equation, or a trigonometric integral, sorry. So I have, integrating this, there's an r squared there. And I'm integrating with respect to r. So r times r is r squared. The integral of r squared, of course, is r cubed over 3. And then we have the sine theta, which is just acting as a constant right now. Okay. And I'm just doing this inner integral first. Plugging in a for r, I get a cubed over 3 sine theta minus 0 over 3 sine theta, which that part will be 0. So it'd just be a cubed over 3 sine theta, and you could factor that a cubed over 3 out. Right? So you'd end up with a cubed over 3 integral of sine theta d theta from 0 to pi over 2. Look, so now I'm going to go and integrate sine theta. So the integral of sine theta is, you have to be a little careful, right? So the integral of sine theta is negative cosine theta. And I'm evaluating from 0 to pi over 2. Cosine of pi over 2 is 0. So I get negative 0 minus negative for the negative part of the cosine. Cosine of 0 is just 1. Okay. So I'll have a cubed over 3 times 0 minus negative 1 and 0 plus 1, which is just plus 1. And then 1 times a cubed over 3 is a cubed over 3. And we just want to do a whole bunch of examples. Okay. Okay, so next, number 9. So we have the integral from 0 to pi, and then the integral from 0 to cosine theta of r dr d theta. Okay, this time we want to sketch the region and then evaluate the thing. Okay, so r equals 0 is the origin. R equals cosine theta is one of our shifted circles. Okay, in particular, what is it? Well, it's cosine will start out here at 1 and then die to 0 and then come back around. Okay, so it's going to be this curve. And it's traced out from 0 to pi, right? So if you need to, you can always start back and draw cosine theta. And it goes up to 1 and down to -1. This is pi over 2, 2 pi over 2, 3 pi over 2, and then 4 pi over 2. So in our graphing paper, if you were to rotate around, let's get some sort of helper circles. So this is at 1/2, and then this is at 1. Right. So in order to draw that thing, given this thing, which is in the theta r plane, you're starting out at 1 when theta is 0. So this is theta 0. This would be theta pi over 2. So when theta is 0, you're out here at 1. And then theta rotates as r value goes from 1 to 0. And it traces out that part, the upper hemisphere. And then from pi over 2 to pi, it's increasing, decreasing to -1. And it'll complete the entire tracing of the circle from 0 to pi. Okay, so from 0 to pi, we get the entire circle traced out like that. Okay, so we're finding the area of this circle here, okay, with this integral. Okay, so let's do that. What do I need to do? I need to integrate now r, so that will be r squared over 2. There's a color pen. So I have r squared over 2 from 0 to cosine theta, d theta. Evaluate this thing, so put in cosines for r squared, and then minus put in 0, so it just be cosine squared over 2. Okay. And then the important conversion formulas that we'll need, the identity that we'll need right here is, let me put it down here. Recall cosine squared theta is 1 plus cosine 2 theta over 2. And then the other one, sine squared theta, is 1 minus cosine 2 theta over 2. Okay. So I'll replace the cosine squared with that identity. Let's factor out the 1/2 first. So this will be 1/2 integral of cosine squared theta. And then I need to integrate with respect to theta. So this will be 1/2. Oh, I forgot to replace it with the identity. So now I'll replace it with the identity. 1 plus cosine 2 theta over 2 d theta. Okay. And then you can factor out another 1/2. You get 1/4 times the integral of 1 will be theta. And then the integral of cosine 2 theta is sine of 2 theta over 2. Okay. When you differentiate something like cosine of 2 theta, you would have to do a product rule, right? So it would end up being negative 2 sine 2 theta if I differentiate it. When you integrate, it's the other way around. It's kind of an inverse operation. So instead of multiplying with a chain rule, you're going to divide, right? So you'll end up with this factor of 1/2. If not, do a u sub and you'll get the same answer. Okay, do a U sub for 2 theta. Okay. Okay, so now I need to evaluate this on the bounds. So I'll have 1/4 times pi plus sine of 2 pi, which is 0, and then minus, plugging in 0, I get 0 plus sine of 0 over 2. That will be 0 over 2, which again is 0. And then up with pi over 4, which should be the area of a circle with radius 1/2, right? So the area of this thing I know from geometry, area equals pi r squared. In this case, r is 1/2, right? So the area in this case would be pi times 1/2 squared, which is pi over 4. And sure enough, we got it. Right? Okay. Let's get another. So here, evaluate by converting. And this one, you'll really appreciate the power of the polar integrals. So evaluate by converting. Right? Okay, so they give you this big monster sum, 0 to 2, integral 0 to x, of the square root of x squared plus y squared dy dx, and then plus the double integral, the inner part 0, the square root of 8 minus x squared, and then the outer part 2 to 2 root 2. And now the inner part, the square root of x squared plus y squared dy dx. Okay, so to convert this, I'm going to have to see the picture, right? So come over here and draw it, and the order kind of tells you the orientation. So I go y equals something to y equals something, and then I run across the x-axis. So the running man is going like this. So I'm going from the graph y equals 0, which is the x-axis, to the curve y equals x, which is the diagonal. And in that case, he's running from 0 to 2, and the integral's first integral case. Okay, so this point right here is located at 2, 2. And then he's running from 2 to 2 root 2, wherever 2 root 2 is. We'll put it right here. And I'm going from the curve y equals 0 to y equals square root 8 minus x squared. This thing has radius square root 8. Okay? And square root 8 is 2 root 2. So it's a circle that is coming, and I've done it so I know it's going to hit right here, and then it's going to go over to here. And so the other region that we're integrating is that region right there. And if you're not 100% on why these guys are intersecting here, well, you just set them equal to each other, right? So I'll have y equals x on one side, and then y equals square root 8 minus x squared on the other. And this should be 2 comma 2 root. So let's do the algebra and we'll get it that way, okay? Okay, so square both sides, x squared equals 8 minus x squared. Add the x squares over, 2x squared equals 8. X squared equals 4. So x is plus or minus 2. In particular, we want the positive one, 2. If you plug 2 into the either equation, y equals, here you'll get y. If you plug it into the equation y equals square root of 8 minus x squared, if you plug 2 into here, you get y equals square root of 8 minus 4, which is square root 4, which again is 2. So the point is 2 comma 2. Okay. Okay. So in polar coordinates, this becomes one heck of a lot easier, right? So the running man orientation is circular now, and as he's running around this circle, the inner curve is just the origin. The outer curve will be r equals 2 root 2. Right? So it becomes one heck of a lot easier. I'll have the double integral. The running man is going from the origin to the curve r equals 2 root 2. That was the radius. Okay. And for the angle, to know how far he has to go, you can use trig. So this is a right triangle right here. Correct? And if you extract that right triangle and take a look at its sides, what do you have? Well, you have a base of 2, a height of 2, and a right triangle. Here's the angle theta. So we know tan of theta is the ratio of right sides of a right triangle, or 2 over 2, is equal to 1. And what angle, when you take the tan of it, equals 1? Well, pi over 4 in the first quadrant. So the running man must be going from 0 to pi over 4. Okay. Then we use our conversion formulas to replace this part. X squared plus y squared is r squared, so I got the square root of r squared. And then I replace dy dx with r dr d theta. Okay. Okay, then I can simplify that guy. Square root of r squared is r. R times r is r squared. Then I need to integrate that guy. So I have the integral of r cubed all over 3 from 0 to 2 root 2 d theta. And then evaluating it. So I'm going to have something that's not all that pretty. 2 root 2 cubed. So that will be 2 times 2 times 2 is 8 from this part of it. And then I'll have root 2 times root 2 gives me another 2. So I'll have a 16. And then another root 2. Right? So I'll have 16 root 2 all over 3 minus 0 d theta. Okay? And then that'll be 16 root 2 all over 3 times theta, evaluated from 0 to pi over 4. And then plugging in pi over 4, the 16 over 4 will just be 4. So I get 4 root 2 over 3 minus 0. And I lost my pi. So 4 root 2 over 3 pi. Okay. Just 2 more. This time we want to find the area between 2 polar curves. In particular, we are finding the volume under the surface, arctan of y over x, but over top of the region given by x squared plus y squared greater than or equal to 1, and then x squared plus y squared less than or equal to 4, and 0 less than or equal to y less than or equal to x. So this region is just the outside of a circle with radius 1. This region is the inside of a circle with radius 2. Okay. So here's a circle with radius 1. It's a circle with radius 2. And this and this tell me I'm working with this donut region here. Okay. And then this, if you look at just y equals x, well, that's a diagonal. And then in particular, if you think I need y to be greater than or equal to 0, well, that means everything in this direction. And on top of that, you need y to be less than or equal to x, where you're talking about everything underneath here. The overlap of all those regions is just going to be this little region here. Okay, okay, so I need to find that. I need to find the double integral over this region of this function. Right? Okay, so I'm going to go polar. I'm going to convert everything to polar. So I'm going from r equals, not 0 this time, but rather r equals 1. That's the formula for this circle. to r equals 2, the formula for that circle. And then my Riemann is running from this angle to this angle here. Okay? So if you're not sure what that angle is, again, you can kind of use trig, form a right triangle, okay? And then consider the sides of that right triangle. So all the points on this line will be of the form x comma x. So I know that this point is 1 comma 1. And if you look at that triangle, here's theta. This side is 1, this side is 1. So the tan of that angle as ratio of sides of a right triangle opposite over adjacent. And again, it's pi over 4, right? The tan of what angle is equal to 1? Well, the tan of pi over 4 in that first quadrant will give it to you. So my Riemann is running from 0 to pi over 4. Okay. And then on the inside of my integral, I'll have the arctan of y over x. But for my conversion formulas, y over x is the same as, well, tan inverse of theta, or rather tan of theta. Okay? And then you have to tack on r d theta, as usual. Okay, arctan of tan, those guys are inverse functions, so those will cancel each other out, and you'll just be left with the double integral of theta times r d theta. And then that's fairly simple to integrate, so I'll leave that integral to you. Okay, we'll look at one more. And this one, the integral is pretty long, so you have to hang in there if you're watching. It's problem 37 in the old book. So find the volume inside the hemisphere. Z equals square root of 16 minus x squared minus y squared. And inside the cylinder, x squared plus y squared minus 4x is 0. Okay, so if you take a look at what this thing is, the cylinder, you can complete the square if you're not sure, right? So x squared minus 4x plus negative 4 over 2 squared, right? It's always b all over 2, and then you square the whole thing. So negative 4 over 2 is negative 2. Negative 2 squared is 4. Oops. Then minus y squared. And on the other side, I'll have to add in another 4. Complete the square, and we get x minus 2 squared minus y squared is equal to 4. And this is a cylinder such that in the xy plane, so in the xy plane, the center is at 2, 0, and its radius is 2, so it looks like this. We're trying to find the volume over top of this and then underneath this. So you imagine you kind of take this upper hemisphere of the cylinder, the upper hemisphere of the sphere given by z equals square root 16 minus x squared minus y squared. On the inside of this, in the xy plane, there's going to be a base of a cylinder kind of situated right here, and it's going to be going up and then hitting this upper part of the sphere in kind of a region like this, and it'll be a cylinder of some sort. Going through the hemisphere. We just want to know kind of the volume of this object, this cylinder part right here, up to this surface of the actual what are we calling this? This hemisphere. Okay, so it's the volume of that thing that we're after. I'll do another picture of it. That thing right here is this thing here. And we want that. Okay, so we're going to have to integrate over top of this region here, which is this region here. Okay. And inside the double integral is going to be this guy right here. Okay, and that'll do it for us, right? So we'll have a double integral of this thing, 16 minus x squared minus y squared dA over top of this region R. Right, I'm going to go ahead and convert it to polar coordinates. So I'll have the double integral. And if you remember, this is the second sort of class of polar curves that are very important to us. In particular, this would be the r equals a cosine theta class. And the a value in this case is going to be this point here at 4. So you get r equals 4 cosine theta in polar coordinates. Okay. Right, so the Riemann man, as he runs around picking this thing up, he's going to have to go from 0 to pi, right? And the graphs go from r equals 0, which is the origin, to r equals this curve, which is 4 cosine theta. So on the inner part of my integral, I'm going from 0 to 4 cosine theta. And on the outer part, I'm twirling around from 0 to pi. Then on the inner part, I'll have this thing, which if you rewrite, noting that x squared plus y squared is r squared, you have 16 minus r squared. And then you have to tack on r d theta. And that'll do it. That's the integral now we have to tackle. Now this integral is a bit of a nightmare to do. So let's dive in there and let me at least do one complicated integral for you. So right now, we need a u sub to pull this off. So we're going to do a u sub for this right here. So u equals 16 minus r squared. And du is negative 2r dr. So we can replace dr with negative du over 2r. Right? Okay, so I'll end up with the double integral of the square root of u times r times dr, which is now negative du over 2r, times d theta. And I'm really worried about this inner integral first. Sorry. So I know the r's will divide out. You can factor out any constant. So negative 1/2 is a constant, so you can factor that completely out of the integral, both integrals. So I end up with negative 1/2 times the double integral, and I'll convert square root of u into u to the 1/2. And then I have du d theta. And then negative 1/2, I have to integrate u to the 1/2, so that would be u to the 1/2 plus 2/2 is 3/2, divided by 3/2, the same as multiplying by 2/3. D theta. Okay, I can factor out that constant, and I'll end up with in front a negative 1/3. I'm going to back substitute my u value, which is 16 minus r squared, into this expression. And I still have to remind myself to evaluate, so I'm going from 0 to 4 cosine theta. And then d theta. Right. Okay, so now I have to substitute in 4 cosine theta and then 0. So I'll have negative 1/3 integral. If you plug in 4 cosine theta, you'll get 16 minus 16 cosine squared theta. And this will be raised to the 3/2. And then minus, when I plug in 0, I'll get 16. When I plug in 0, I'll get 16 minus 0, which is 16 to the 3 halves, which is 16 to the 1 half, which is 4, and then 4 cubed is 64. You can clean this part of it up using your trig identities. Okay? So 16 minus 16 cosine squared, what is that? Well, that's the same as 16 times 1 minus cosine squared. 1 minus cosine squared from our trig identities is just sine squared. So this will be 16 sine squared. And then if you raise it to the 3 halves power, well, you can think of this as raised to the 1 half power and then cubed, right? So if you do this to the 1 half, you'll get 4 sine theta, and then cube it, you get 64 sine cubed theta. Okay, so I'm going to replace that part of it. And I end up now with the integral negative 1/3 times this integral of, what did we have then? 64 sine cubed theta minus 64 d theta. For this guy, some people may be tempted to do a table or something like that, but I'm going to just kind of use some trig identities to pull it off. So negative 1/3. You can factor out the 64 if you don't want that floating about everywhere. I'll note that sine cubed is the same thing as sine squared theta times sine theta. And I'm going to split this into 2 integrals. You have to be real careful, though, because there's so much floating around at this point. It would be normally minus the integral of 64, but I have to distribute this negative 1/3. So it's going to be plus 64 thirds, and there's a d theta on this, and this will be integral of d theta. So hopefully that's not too confusing. On this part of it, I'm going to do a Pythagorean conversion into 1 minus cosine squared. Okay. I can go ahead and integrate the second part. And when I integrate, I'm going to put it up front. Okay, so it's going to be 64 thirds theta. And I forgot where I'm evaluating. 64 thirds theta from 0 to pi. Okay, so this first guy is 64 thirds theta from 0 to pi. That's this part. Okay, and then this part, I'm writing minus 64 thirds integral of 1 minus cosine squared theta times sine theta d theta. Sorry for smushing that. And then I'm going to do a u sub. Okay, so I'm going to let u equal cosine theta, and then du will be negative sine theta d theta. Okay. So when I substitute in here, here's the sine theta d theta, but I need a negative version of it. So I'll just put a negative in there as well. And I could factor that negative out in front, so this will end up being a plus. So I'm doing a lot of steps at once. Hopefully it's not too confusing. If I evaluate this thing, it'll be a pi in there. So I have 64 thirds pi. That part's done at least. And then again, this part, because there's that negative from the differential substitution, I have to kind of factor that out. This will become plus 64 thirds. And then I have the integral of 1 minus u squared, I du. And then I can integrate this thing. So this will equal 64 thirds pi plus 64 thirds times u minus u cubed over 3. And remind myself to evaluate. Okay. Back substitute. So back subbing, I'll get the first guy 64 thirds pi and then plus 64 thirds times cosine of theta minus cosine cubed of theta all over 3. And I'm evaluating this part from 0 to pi, I believe. So this will be 64 thirds pi plus, if I put in pi into this thing, what do I get? Well, I get 64 thirds times cosine of pi is -1, so I have a -1 minus cosine of pi, -1 cubed is -1. So I'll have -1, which is +1, all over 3. So this will be plus 1 over 3. And then minus this thing evaluated at 0. So cosine of 0 is 1. Minus cosine of 0, 1 again. 1 cubed is 1, so minus 1 over 3. Okay. Almost there. 64 thirds pi. And then all this junk, plus 64 thirds times -1 plus, well, it's -1 plus another -1 is -2. And then we have a 1/3 plus 1/3 is plus 2/3. Then we can find a common denominator here. So 3, this will become 6. So -4/3, and I'm getting a huge number. So 64 pi over 3 plus 4/3, so 64 times 4, 16, 256. So plus -256 over 9. Okay. All right, so they can be pretty nasty. You get a lot of practice doing integrals, make you good at doing integrals. I don't know if you put that on your college resume or on your resume if you go to get a job. I want to get a job working for Amazon at this point, but it'll prepare you for your future engineering classes. Okay? Okay, great. See you next time.